The second speaker is Professor Egor Babaev from KTH Royal Institute of Technology in Sweden. Yes, let me introduce him for briefly. He received his PhD from University of Uppsala in Sweden in 2001. And then since 2008, he has been working in the Department of Theoretical Physics in the Royal Institute of Technology in Sweden there. And also he had worked in Microsoft Station Q as a consultant from 2016 to 2021 recently. And he is expert on the superfluid state of matter, especially the multi-component condensate and the multi-band superconducting systems. And so today he will talk about the type 1.5 superconductivity and theory and experimental evidence. Please welcome him with a big hand.
Thank you very much for the invitation and for the kind introduction. Just to double check, so how much time do I have before the question session?
You have 45 minutes.
45. Great. So then I will. So thank you very much. So I'd like to thank you, and I will outline our series of work, which was done with many students and collaborators, Ewan Karlström, Julian Garot, Michael Selaev, Martin Spide, but also with many others, about subjects that experimentalists termed type 1.5 superconductivity. And let me see. So let me go to the demonstration mode. And now I lost my, cursor. So let me do different. So let's see. Okay. So let's see. Can you see my mouse now also?
Yes, we can see your mouse and your screen, but there is an alarm notice something.
What do you say? Is there some problem?
In the middle of at the center of your screen, there is some kind of window saying something, which is very small. I cannot see. But...
this movie can't be added.
Okay. Okay. It's okay. Yeah.
Some movie couldn't be converted.
Oh, there is some message. Movie can be converted. I see.
That's what it says.
Okay. That is.
Yeah, it says it like that. Yes.
So let me try then to do. Just to do something. For now, it is actually completely frozen. It seems like could not. Oh, that's really strange, actually. So, okay, so let me try to do something else. So okay, let me see. Let me try to reshare that. Is there now? Do you see now this extra message, or is it good now?
We can see your screen, which I think is the keynote app, not the presentation mode yet.
Do you see this extra window, or is it now? Okay. Do you see this extra message? You say there was some extra message in the.
There's no other message.
Okay.
The message window is gone now. Yeah.
Okay. Good. Great. Okay. So let me then. Okay. So then so let me remind you very briefly. So what is usual classification of superconductors? So historically, first superconductors that were discovered are type 1 superconductors. And in external field, they have a macroscopic separation in the normal and superconducting domain, so-called Landau pattern. So here, just some textbook picture of a type 1 superconductor in an external field, and shaded areas are superconducting, while the areas some sensation for me. I'm actually losing sometimes. I don't see my own cursor. So cursor is okay.
Yeah, we can see your mouse.
Yeah,
Yeah.
it also works for me. Great, yeah. So, and then the white areas are normal. Then you can see these are macroscopic sizes, that's this 1 centimeter bar. And so why these are so large is because the interface tension between normal and superconducting state is positive, and this is like some non-equilibrium pattern usually, but the system wants to minimize the surface area, so there are this superconducting inclusion in the normal state. Vice versa, the system wants to make this boundary as small as possible, and hence leading to some kind of macroscopic pattern. And now this was basically to explain this type of behavior. This was the motivation of introduction of Gisborne-Landau model that everyone knows here. So this is just a model for complex field, and the main new thing about this model that was introduced by Gisborne and Landau was that they let this complex field modulus to vary in space. And in case of constant modulus of this complex field, we have a London model that has degrees of freedom phase and vector potential that was discussed in the past by London, and Landau introduced also modulus. Gisborne and Landau introduced also modulus as a dynamic variable, and then introduced a second fundamental length scale in superconductivity, the coherence length, the length at which this modulus varies, while London introduced magnetic field penetration length as the length at which the magnetic field decays. So, and then the argument was that there is a positive and negative interface energy. So there are two fundamental length scales in superconductors, and depending on the ratio, they calculated that if there's some 1 over square root of 2 dividing kind of value, then if the ratio of these two fundamental length scales are smaller than this, in type 1 superconductor, these domains want to be as large as possible, or preferably system should have a monodomain. And if coherence length is larger than size, and this type 2 superconductors, and then say that the interface energy becomes negative. And if there is some excitation that causes negative energies, and the system wants to go, just a signal that system wants to go to a different state, but they didn't elaborate on this extra state because of they saw there was no evidence for this type 2 superconductors. So this is quote for the paper where they actually introduced the concept of type 2 superconductors. And then actually the story was that it was actually, there was experimental evidence, very solid, about the existence of type 2 superconductors. In 1937, it was discovered by Shubnikov that it was well before Gisborne-Landau work, but it was actually not, very few people believed in that. And and then so basically it was Shubnikov was executed in 1938. He was accused to be a spy and executed, and then basically for decades like there was no spokesperson for existence of type 2 superconductivity. Okay, so now we all know about quantum vortex. In this conference it was recurring topic. I will so basically the main thing is the main concept is by Onsager and Feynman that if you have complex field, the phase could change by 2 pi, and that's the topological defect vortex. And corresponding situation in superconductors was considered by London, and then basically said, okay, there is phase winding, then you carry one flux, one quantum of the magnetic flux. Okay, so now, so basically a combination of these ideas was done in Abrikosov work, and then he says that, okay, like if there's negative interface energy, then this new state that arises is a vortex lattice. So in principle, this is basically similar type of vortex lattice as was a vortex state that was considered before by Onsager for and Feynman for superfluids, except they did not talk about vortex lattice. They just talk about some density of forces that arises under rotation. And here another thing is that there is first critical magnetic field as a concept of that was first appearing in Abrikosov, that magnetization of superconductor is actually has two critical fields. First where vortices appears, and second where superconductivity disappears. And these are all second order phase transitions. So magnetization of superconductor, where is at first superconductors display perfect diamagnetic response, currents only on the surface. And then vortices penetrate and the magnetization drops, the magnetic response becomes worse, and then so basically there is this type of phase diagram, and then if you have negative interface energy, superconductivity can persist above thermodynamical critical magnetic field, and that's because you have some objects with negative energy, when you phase separate into superconducting state and normal states that living in the vortex cores. That this basically can think about it in that type of framework that was interpreted as some objects having negative free energy, and that allows superconductivity to survive above the thermodynamical critical magnetic field associated with uniform state. Okay, so and then like on the one hand, that seemed to be quite generic classification of superconductors because of, let's say, okay, this like it's an energy argument. The interface energy could be either positive or negative, and then if you start generalizing models to more complicated ones, you still would get either positive energy interfaces or negative energy interfaces. Even you have, like, let's say, multi-component Ginsburg-Landau model, and that seemingly would furnish still a very good classification. However, I will be arguing that it's not so, and there is one aspect. There's actually one important aspect which is missing in the original Ginsburg-Landau argument. That in general you cannot have two like dichotomic classification of superconductors. And let me make first observation is that like, okay, let's in general superconducting state breaks more than one symmetry, and then by definition in general you don't have a single coherence length. So then the state which is possible, so if we have multiple coherence lengths, break, for example, multiple symmetries, then there must be a state where some of the coherence lengths are smaller and some are larger than magnetic field penetration lengths. And then what kind of superconductivity is that? And like is it type 1 or type 2? And that is things that we started to explore like almost 20 years ago. And let us consider the very simplest example. And like most of the materials of current interests, they are multi-band superconductor. You have multiple electronic bands, and each of the band you can form superconducting gap. And then the simplest possible generalization of Ginzburg-Landau equation to superconductor with two auto parameters, two complex fields. And that was known for more than half a century. And then like you may even have like multiple fields, but still only single broken symmetry if you have Josephson coupling between components. Now, other type of models that were considered for a long time, also almost like half a century, are the systems where intercomponent Josephson coupling is forbidden on symmetry. And that was not only something considered in superconductivity, but also like in nuclear metals, for example, protonic sigma minus Keperonic condensates are supposed to coexist certain depths inside a neutron star, metallic hydrogen, and so on and so forth. So let us look, for example, let us take a simplest possible example. Simplest possible generalization of a system that breaks more than U1 symmetry, and that is like the case of two independently conserved condensate. Think about it as, for example, protonic and sigma minus Keperonic condensate in neutron star, but there are also like condensed matter realization of such things. And then there is one magnetic field penetration length. So basically, you have two independent condensate, but they are coupled by still same vector potential. So there is one single magnetic field penetration length, but then there are two different coherence lengths. So now, what does it mean? What are the consequences? Like if you start covering all the hierarchy of the length scales, and first we need to classify, take this U1 cross U1 model and try to understand what is the simplest possible topological excitations into component superconductor. And the simplest possible topological excitation is the one where phase winds phase of, let's say, psi1 winds by 2 pi, by psi2 doesn't wind by 2 pi. Now, so there's one important consequence of the fact that two condensates are coupled by the same gauge field, and that relates to energy. There's one important energy aspect of topological excitations. And to see, the easiest way to see that, and that was, if you want like detailed discussion, there's like PRL from 2002 that discusses in detail vortex energy. So let us take a London limit. Let us assume psi's are constant, and then let us just rearrange the terms in this model. Just separate variables in the gradient of the phase difference of these complex fields and all the other terms. And now if you separate variables like this, you can see that the first term resembles the gradient term of a neutral superfluid. There is no coupling to vector potential. And we know that in the superfluid, you have like vector potential. If you have no vector potential and you have 2 pi winding in the phase, then if you integrate this term over two-dimensional space, for example, that will have logarithmically divergent energy. And here there will be also some contribution from the gradient of the phase, but that can be asymptotically compensated by vector potential. And so these in that part have finite energy per unit length. And this term will give logarithmically divergent energy. So then elementary excitation, the simplest possible topological excitation in we form is will have at least in a multicomponent superconductors at least logarithmically divergent temperature. But you can form actually more complicated topological excitations where both phases bind by 2 pi. Then this term is identically 0, and then these terms have finite energy. So that's important for what follows, that you will have so basically composite bounds states of vortices have finite energy, but elementary have infinite energy. And there's like very simple calculation that, for example, for detailed calculation can be found in this paper, but in other places. But so if you just use absolutely standard calculation for magnetic flux of an ordinary vortex, you just write current and component I, superconducting current in component Y. So now there is gradient only in phase winding only in component Y, but not in the other component. Then current has this prefactor. And then if you want to calculate flux of a vortex, you integrate over contour of the vector potential. And then you find that this elementary vortex carries this type of fraction of magnetic flux quantum. So, and it costs logarithmically on a more general model linearly divergent energy per unit length. But now, if you have another phase binding in the other phase, then the fractions will add up to unity. The fractions of flux quantum will add up to unity, and then integer flux vortex has no gradient to the phase difference. It is finite energy objects. It's finite energy object. Hence, basically, what happens is that you have the vortex structure is that you have 3 length scale in the vortex. So if you apply external field, the normal external field would produce only integer flux vortices in this material. There are cases where you can produce by external field fractional vortices, but that's like I will not touch on this more complicated cases. But in this simplest model, you produce integer flux vortices where 2 fractional vortices are electromagnetically confined, and then you have this basically large vortex core, and you have another component with small vortex core, and like if you have this type of hierarchy of the length scale, and the magnetic field is localized in between. Okay. So now let us consider a pair of such vortices, and this like what I show the picture is just cartoon. It's not a solution, just illustrative cartoon. And then you take a pair of such vortices widely separated, and you start bringing them together. And essentially, first they will start filling each other's large pores that exist on the large coherence lengths. And that's like they will be interacting by this. It is like some kind of like a generalization of a matrix effect. You put you have a trampoline and you put 2 basketball on a trampoline. They will suppress membrane and they will move close together. So and then or like if you have 2 things on a matrix, on a Sagi matrix, they will move together by basically suppressing a matrix. And similarly, here, or we can calculate that intervortex interactions will be a sum of some Bessel functions, and so the vortices will attract. And this is interaction energy now coming from numerical solutions. At the large length scale, they attract. And then when they attract up to the point where they start feeling magnetic field of each other, then they start repelling. And therefore the non-interaction is like non-monotonic, long-range attractive, short-range repulsive, if you have this type of hierarchy of the length scales. This is numerical solutions. So if you take basically some initial guess of 9 vortices, this is basically coarse in component 1, coarse in component 2 with slightly larger density. This is current in component 1, current in component 2, and this is the magnetic field, which is like intermediate length scale. You minimize energy, and then you get basically a vortex cluster. And here, like nonlinear effects are important, and in this case, you see that form a vortex cluster where one component has vorticity, and the other component relegated almost all of its current on surface of the cluster, and one component has a well-defined vortex cores, and here there are also vortex core and second component, but you basically cannot see them. It's almost like one mega vortex. So in general, it is so basically this is what happens with currents in numerical simulations. So there's now currents simulated by vortices, and then you basically see the existence of 2 types of tendencies. So one tendency is to form a type 1-like behavior that basically to make this cluster as round as possible because of this extra current on the surface of the cluster. But inside it wants to create as much interface as possible. And that is basically illustrates that the Ginzburg and Landau argument is not generic because of they assumed that you can classify superconductors by one-dimensional interface. So this thing with like whether interface energy is positive or negative, this is only the consequence of assuming that interface is translational invariant along the interfaces. Translational invariance can be placed by 1D. And in general, like this example shows that you generally have like infinitely many complicated interfaces. Like let's say inside the clusters, the interfaces have negative energy. It wants to create as much kind of phase separation and vortices as possible, but the interface of the cluster itself has positive energy. There are also some effects of non-pairwise intervortex forces. I will skip. I have much more kind of other materials. I will skip some of the slides. But in general, I should say that you have basically all various kinds of clusters forming in this type of systems, and but the bottom line is that you can have like complicated cluster structure where non-pairwise forces play important role, but in general you have like the presence of both negative and positive interface energy. So so basically as a phase diagram of a superconductor, if you move away from this simple one component model, it has basically not just normal state, vortex states, and Meissner state, but it also allows phase coexistence, microscopic phase separation between the vortex clusters and normal domains. And then there is like first magnetization curves is In that case, it is the first order phase transition at the first critical magnetic field, where a system goes into macroscopic phase separation into vortex clusters and Meissner state. Now, there are a couple of aspects that I will very briefly mention them, but I will give references to detail. So, what about all kind of intercomponent couplings? So this was the principle was illustrated by this U1 cross U1 model, but most of the materials of current interest, they are multiband, and then there are multiband couplings, and all these couplings were considered both on the Ginzburg-Landau model and on in all the fully macroscopic models. You don't need to rely on Ginzburg-Landau models. I will just say briefly how it works, how you treat all kinds of intercomponent coupling. Let us consider the most general model. So you can have most general gradient terms in principle and most general collection of the potential terms. How does one calculate coherence lengths? So in that case, you follow the standard procedure, but in a more mathematically complicated way. You consider, so fundamentally the coherence length is the exponential increment with which the density recovers from perturbation. So you need to consider small perturbations in all fields around the ground state values, both in density fields and the vector potential, and then linearize theory in these small perturbations. And in general, you will get some quite complicated linearized theory with all kind of cross couplings in between small derivation, where this is the Hessian of the field. But then you write all these terms, you collect these terms, and you diagonalize. So, for example, let us consider very simple gradient term, but most general potential terms. So you expand the small perturbations, you get some cross couplings, and then you go to linear combination of the density fields that eliminates cross coupling. And this defines the new coherence length. This is kind of very common misconception of superconductivity, that if you have multi-band superconductor, you still can identify coherence lengths with band 1 and band 2. No, you cannot do it. Basically, your coherence lengths they are associated with various kind of linear combinations of the gaps, and then you can calculate them. But at the end of the day, so once you diagonalize this and introduce new coherence lengths, so this is just inverse of the coherence lengths called also mass of the field. Then your intervortex interactions will become will have identical form of like multiple Bessel functions, and then all this typology, including type 1.5, is possible. So I will skip this technical detail of concrete calculation. I will also skip how it works microscopically, but I will give like a little just I will outline the results of microscopic calculation of coherence lengths in two-band models. So if you have two completely decoupled bands with two critical temperature, 1/2 and 1. So here one component condenses, other component condenses. The dotted lines are two coherence lengths. You have two critical points. One coherence length will diverge at one critical point, second coherence length will diverge at the other critical point. And these are inverses of coherence lengths are plotted, and you see here two divergences. Now, if you introduce interband Josephson coupling, you calculate coherence lengths, and they are given by this type of red curve. So then there's no Josephson coupling breaks symmetry explicitly down to U1. There is no divergent coherence length any longer, but it can have a maximum. And the other thing is that here avoided crossing is formed. But main thing is that coherence length behavior is strongly non-monotonic. And like if you would have U1 cross U1 and divergent coherence lengths, then there will be a generic breakdown of type 1, type 2 dichotomy at second critical point because of the coherence length divergence. Second coherence length divergence, you have superconductors with multiple critical points. You cannot be, except for special cases where coherence length is not felt by vortices, you cannot be actually type 2 superconductor near critical points like this. But if you have interbands on coupling, it's not guaranteed that you fall out of type 1, type 2 dichotomy near a critical point, but there is a maximum in coherence length. So I will skip the microscopic calculations, and I will talk about what is the experimental evidence. The first proposal of experimental material of this type was proposed by Viktor Mashalkov in MGB for MGB2. There is still no theory calculations for MGB2 of no reliable theory calculation of what are the coherence lengths in MGB2. So, but they basically saw the vortex clusters in this material. This is the first paper, and they also introduced the term. So, another material where there was more activity recently is strontium ruthenium oxide. And there basically every group that studied vortex vortices in this, they saw vortex clusters. So vortices form this kind of fancy vortex clusters. And then it was voiced for a long time that there is inter-vortex attraction. But what is more interesting, there is a paper that didn't say anything about inter-vortex attraction, but there was like long forgotten paper that they saw that they have zero vortex creep in strontium ruthenate, but without any kind of increase in critical currents. That is precisely means they have like very different type of interpretations. They didn't talk about with the solid inter-vortex forces are usual repulsive and stuff, but it's precisely what should happen if your vortices form clusters, have attractive interaction. Then there is no vortex creep. They're not repelling each other out of sample in zero field. They stick to each other, but also we can move these clusters easily by current. So there is no this is not a self-contradictory statement as was thought before. That we may basically have zero creep and no increase in critical current. But the main evidence comes in 2014, where the measurement was done with muons, and they observed in muons phase separation in the vortex clusters and normal domains. But most importantly, I'm running out of time, so I will not cover all data, but will basically highlight the most important thing. So basically, if you cool strontium ruthenate in external field, and you analyze with muons a fraction of the sample containing magnetic flux, and then you see if you cool down below TC here, you see first of all phase separation. So basically, sorry, yeah, this if you look at this thing, so basically cool below TC, and then it's not like you dilutely get more and more superconductivity and you uniformly dilute vortex lattice more and more, but rather you get phase separation in the fraction of the sample that contains flux that drops, and fraction of the sample in the Meissner state. So that's consistent with the semi-Meissner state. It's consistent with the phase separation I talked about, but it also phase separation could happen for other reasons. If sample is bad and you have pinning defects, you can have basically this type of phase separation for artificial reasons, for pinning castles. But then this experiment have shown that it is not pinning, which is at play. What they did also, those experiments, they extracted, if you focus, you look at this phase separation, and you focus on local magnetic field inside this vortex clusters region, and you measure its temperature dependence, and you see that first it drops, but then it increases with decreased temperature. That is very significant thing, because it means that not only you phase separate into Meissner and vortex droplets, but you also, as a decreased temperature well below half TC, this vortex droplets start contracting. So if it would be just vortex droplets formed because of pinning, they will get pinned, and they will basically stay pinned, and you decrease temperature, they're getting pinned better and better. But instead, you decrease temperature, this vortex droplets start contracting. And I told you what I told you before, that if there is some kind of second critical point, there is a divergent coherence length, and the type 1, type 2 dichotomy is either broken generically near that critical point, or if you don't have critical point, but you have a weak interband coupling, there is a maximum coherence length. And that's also highly, so basically these are inverse coherence lengths, these curves. So basically if you cool down, there is a growing coherence length, and you start falling deeper and deeper in type 1.5 region, and that exactly gives this type of magnetization curves. So basically that is like fully consistent with type 1 superconductor, type 1.5 superconductivity, and that cannot be explained by pinning. And also that signals that either there is a competitive pairing channel, a system is close to some other phase transition at low temperatures, or it has weak interband coupling. Okay, this is just like this is on this part is a microscopic calculation of inter vortex forces. So Boom, how many minus do I have? Yes.
Yes, you have a couple of minutes. Yeah.
Okay, couple minutes. Good, and then I will flash a couple of other results, but without explanation, just to tell like give reference to tell what other things happen. So another type of system where type 1, type 2 dichotomy should be generically broken is S plus IS superconductors. So basically, if you have broken time reversal symmetry of some kind, so here you have U1 symmetry, superconductor, as a function of doping, and here you break time reversal symmetry. Also, you break extra symmetry on this transition. So basically, it can be calculated that although if you break time reversal symmetry in S plus I, S plus IB superconductor, you also have divergent coherence lengths at this phase transition, and then you also form vortex clusters. So basically, also like near this transition, the type 1, type 2 dichotomy doesn't work. Then what is more, another type of thing I wanted to mention about these vortices is like if you have ordinary vortex method, this is was well investigated, and then if you have impurities in ordinary vortex method, you can have vortex glass if and only if you have you add impurities. But what is also interesting about type 1.5 regions is that you can form vortex glass in certain conditions without any quench disorder, without any type of impurity, just as a consequence of interband just intervortex forces. So basically, this was another our work. We can show that you can form glass, vortex glass in a translationally invariant clean system just as a consequence of interaction forces. And then, as a type of example where you can break extra symmetry and break type 1, type 2 dichotomy dirty S plus minus superconductors. So this was demonstrated fully microscopically that by adding impurities you can break time of symmetry and hence also have divergent coherence lengths. And so basically the break type 1, type 2 dichotomy generically. So that basically summarizes, if I summarizes the difference between type 1, type 2 superconductors. So in type 1.5 superconductors, there is a different hierarchy of the fundamental length scale, and in general superconductors they break more than one symmetry. There's more than one fundamental length scale. And there is like new hierarchies that leading to long-range attractive, short-range repulsive thing. And then there is a microscopic phase separation. And there is like many other consequences that I list on this conclusion side. But basically we start digging into the state of this type of hierarchy of the length scales, then there are many other effects, and one of them is vortex glass formation in a clean system. Then there is anomalous vortex viscosity in type 1.5 regime, when there is like becomes especially anomalous near the new type of vortex viscosity mechanisms, for example, in S plus IS transition, in S plus IS superconductors. That especially pronounced near the second critical point. The phase transition beyond mean field approximation is neither of Halperian-Lubin type nor of Dasgupta-Halperian type, but there's like a different thing with first. There's like fluctuation-induced first-order phase transition in the systems where mechanism different from Halperian-Lubin schema. So in general, also the vortex, the phase separation to vortex clusters and normal state also leads to phase separation in domains with different order parameter symmetries. Because of existence of the large cores, they can lead to inducing different symmetry, different type of superconducting order near vortex clusters, and hence you may have, let's say, not only phase separation and in the vortex clusters, but it could be that near vortex clusters, you have S plus IS superconductors, every time reverse symmetry is broken in the Maxwell state, you can have S-wave superconductor. And there are many other consequences. So that's yeah, I think yeah, this concludes my talk, and thank you very much again for the
thank you. Yes, thank you. Okay, now we it's open for question. Yes, Professor Hyung-Sun Choi. Yeah.
Oh, I was just clapping.
Ah, okay. Sorry, I just confused with that hands up and then clapping. Yeah. So now it is open for question. Yes, Professor Saegwon Kim. Yeah.
Thanks for the nice talk, Igor. So I have so you mentioned this non-pairwise vortex interactions somewhere. Can you tell us more about that? Well, what do you mean by non-pairwise interaction between vortices?
Right. So basically, like superconducting models are nonlinear, and the usual vortex forces, which are considered in, let's say, type 1 or type 2 superconductors, so they usually considered in a linearized approximation at long ranges. And that is entirely sufficient. That is entirely fine because there's no monotonicity and this type of things. But in general, since the system is nonlinear, then if you have vortex cluster of two vortices and you get third vortex in, your interaction will be modified by these two because of nonlinear effects. And this we investigated. That's also true. There are nonlinear forces, nonlinear effects and intervortex forces already also in ordinary superconductors, but they don't have that many. They're not really important in ordinary superconductors. But if we have these vortex clusters, they're tightly bound. Then if we also consider fluctuations, etc. Then actually this nonlinear effects leading to three-body forces, four-body forces, they become important, and we kind of calculated them. And in general, since these are nonlinear effects, you can calculate it only numerically. This is example when you pin two vortices numerically on these things, and you move in the you bring in the third vortex, and you measure. So basically, here the lower panel, you measure basically the difference between pairwise forces and real forces, and you can extract their three-body forces, and they can actually affect in general structure formation.
Is this strong enough to change phase boundary significantly?
Could you please, yeah, could you please say again?
So is this non-pairwise interaction strong enough to change phase boundary from classical picture?
Yeah. So this does not, in the cases that we know at least, it doesn't change phase diagram, but it affects the structure of the vortex cluster. So basically, like if you solve full nonlinear problem, they are not a real superposition. Like superposition doesn't work. They're actually more complicated than just superposition forces.
Okay. Yeah, thank you. Thank you very much.
It's Professor Sakbam Jung. Yes.
Yeah, thank you very much for your talk, Egor. It's nice to see you again, even by Zoom. But yeah, my question is about, like if you have vortex lattice in this type 1.5 superconductor, I mean, I guess one characteristic feature would be like how the stability of this kind of lattice would actually depend on the the lattice parameter, but without changing the lattice constant, I mean, would there be still some way to identify these, to figure out whether this is type 1.5 stable, just by looking at the collective, for example, just by looking at its collective mode?
I didn't hear clearly the last sentence. If you could please repeat it.
Yeah, I mean, without changing the lattice constant of the vortex lattice in this type 1.5 superconductor, could you suggest any way of actually what experiment you can actually do to figure out that this is indeed type 1.5?
Or if I hear correctly, you also mentioned normal modes, right? Collective modes.
Yes.
Oh, that's excellent. Yeah, that is excellent question. Yeah, that's a very, very nice question, because actually you can detect whether the system is in the type 1.5 region without vortices, and that is by studying actually collective modes, not generically, but in certain cases. And the main reason is, maybe I should have some slides here. So basically, it's not really collective modes I will be now talking about, but almost, but not quite. Something without dynamics, but I will tell about something without dynamics, not legged modes, but it's actually, it is de facto related directly. So, and so what I mentioned to you, like previously, a simple example, if you have interband coupling and you introduce small perturbations in densities, then there are two coherence lengths associated with different linear combinations of the gaps. And then there is also another mode, which is not important in the two-band case for vortex interaction. This is legged mode associated with the phase difference mode. So we treated for vortex states, we treated mixed density mode, and there are separate mode for phase differences, which are not important. But if you actually do very small modification of the model, if you have broken time reversal symmetry, then strictly speaking, there is no legged mode in the usual sense, because you start mixing densities and phase difference. So basically, your legged mode becomes mixed with amplitude modes. And that you can measure basically, and by that time, since that means, since as a mixed with density modes, that means this mode will be also the mass, the inverse mass of this mode will determine vortex core size. So basically, and also, this example shows, for example, just calculation of normal mode for dirty S plus minus superconductors. So these are small deviation in phase in the modulus, sum of the modulus, the difference of the modulus, and phase difference. And these are what kind of linear combination of them constitutes normal modes. And there, here you see the linear combination. So legged mode becomes mixed with relative density mode, even at the level of linear theory. Linear classical theory is mixed. And then this basically the masses of this mode diverge near symmetry breaking phase transition, and that you can see in principle through measurement of like how usually legged mode is measured, and that will kind of show softening of the legged mode, but also that means it directly implies that vortex cores blow up. So basically, yes, so that's basically this softening of the Leggett mode translates to divergent coherence. Softening of the normal mode, if it is Leggett mode mixed with amplitude modes, it directly translates to breakdown of type 1, type 2 dichotomy.
Okay, thank you very much.
Okay. Okay, if there is no more questions, let's thank the Professor Babaev again. Okay. Thank you.
Thank you.